As we begin this video, we're going to review something that might be a new topic to many of you. It's the idea of a Venn diagram. And the reason we want to start here is even though this isn't a focus of our class, this is where many of the ideas from this section kind of grow out of. So if we begin with this visualization, the ideas might help stick in your mind. And if so, that just helps you remember the upcoming formulas. If this visualization is not helpful, realize that as long as you memorize the formulas and know how to work with them, as we'll go through many examples, that's really all you need. This beginning discussion is just maybe an additional attempt to give some meaning behind where these formulas came from. So what you're looking at here is a Venn diagram, and as an introduction to it, or perhaps a review if you've seen it before, we see it's made up of two shapes. First is this rectangle, which is encompassing everything. And you can see I have the exact same diagram duplicated below. And the rectangle is our universal set. Often there will be a U in the upper right corner to indicate universal set. And what that means is this is basically our universe of discourse. Everything that we care about occurs within this rectangle. Now here, although all we care about is what's inside this entire rectangle, we could see the rectangle is split into things that are a part of this circle and things that are not a part of this circle. So there's two distinct parts to the universal set. Either something's in the circle or it's not in the circle. Now we see our circle here is named E, and again it's just duplicated below. So one thing that happens with Venn diagrams is we like to shade certain sections, and these ideas of these subsections in set theory is called subset. So here E is a subset of the universal set U. So if I was asked to shade E in the Venn diagram, I see E as this entire circle, so I would carefully shade everything inside the circle. Let's do that. And here in light blue, we see everything that is part of E is now shaded. Now in the diagram below, let's think about kind of the opposite of that. If we don't want to shade E, in fact, we want to shade what's outside of E. Let me write that down. So next in the bottom diagram, we want to shade everything that is outside of E. So that would be everything outside the circle, but still in the universal set. Let's shade that here in pink. So here in pink, we've shaded everything outside of E. Now in set theory, a certain branch of mathematics, we have a particular name for everything outside of a set. That's called the complement of the set. So everything outside of E is the complement of E, which we use a notation E, and then we've got a superscript C. So we would read this left to right as E complement. So what we've got shaded here in pink is our E complement. Now where this is going to relate to probability is we're going to start talking about, let's consider the probability of a certain event E. Then the probability that E occurs is some number. And then we could also talk about the probability of E not occurring, or what's the probability of the complement of the event. Now the way these two ideas get linked together in a formula comes from the idea of what happens if you add everything in E plus everything not in E. So watch this. As I grab everything in E, and I combine it with everything in E complement, what do you see has occurred to the picture in terms of shading? When you take everything in E and you combine it with E complement, let's watch that one more time. So above we had E shaded, below we had E complement shaded. When I combine the two together, we see that we get the entire diagram shaded. All of U is now shaded when you combine E plus E complement. So E plus E complement is the universal set. It gives you everything. And then whenever we talk about probabilities, it turns out the probability that the event occurs plus the probability that the event doesn't occur, which in notation is the probability of E complement, that is equal to the probability of the entire universe. So we've covered all our bases. We say the probability that it occurs plus the probability that it doesn't occur If you have the probability that it does plus the probability that it doesn't, you have all possibilities. And whenever you have all possibilities, you've got 100% or a probability of 1. So this is the main formula that we're going to work with whenever it's in regards to an event or an event's complement. And again, this beginning was just to help us visualize where does this formula come from. Now let's look at the related formulas, and then we'll just start working and solving some problems with these ideas. So here, let's let E be an event that could occur. The concept of E not occurring, like we just discussed, is the idea of the complement. So E not occurring is the complement of E, which is written as E superscript C. And as we discussed earlier, we have these formulas. So we have our original formula here, and then the other two are just algebraic manipulations off of this. So this first formula at the top tells us the probability that E will not occur, the probability of E complement, is equal to 1 minus the probability of E. So if you know the probability that something will occur, to figure out the probability that it won't occur, you just take 1 minus the probability that it will. This next formula is the formula we started with. It says the probability that something occurs plus the probability that it won't occur altogether is 1. And then our final manipulation is the probability that E occurs is equal to 1 minus the probability that it doesn't occur. Because remember, whenever you see E complement, we're to read that as E not occurring. Let's work with some of these formulas. And these are formulas I'd encourage you to either memorize or write down on your personal note sheet for the upcoming exam related to this chapter. So in the next example, we have if the probability of A is 0.35, so the probability that event A occurs is 0.35 out of 1. Find the probability of A complement. So remember, A superscript C is read as A complement. We know the formula that the probability of the event plus the probability of the event not occurring, A complement, is 1. We know that the probability the event occurs is 0.35 plus the probability that the event does not occur is what we're looking for equals 1. Well, let's substitute in the values. 0.35 plus the probability that it doesn't occur altogether adds to be 1. Here you might be able to just see what it is with mental math, if not do some algebra. You want to get probability of A complement by itself. It's currently being added by 0.35. So you subtract by 0.35 to both sides. What's done to one side in algebra must be done to the other to keep them truly equal. Cancels on the left side. We get probability of A complement is equal to 1 minus 0.35, which is 0.65. So the probability that it does not occur is 0.65. And that's the probability of A complement. Now you'll notice that the first thing I did when doing this problem is I wrote down the relevant formula. I think this is a good idea as you go through your homework because immediately you're pulling to mind the important formula, you're writing it down, practicing helps pull it to mind quicker, and it will also just help you naturally memorize it the more you work with it. So each time you do these type of problems, write down the relevant formulas. Now our next example, I would encourage you to read through it on your own, pause the video, and attempt it on your own. After you've attempted it, unpause the video, and then we'll work out the solution and you can check your work to see if you did it correctly. So pause now and then unpause to check your work. So reading this through left to right, I can see that it says the probability of B and then the superscript here, C, means B complement. So I know in words this is the probability that B does not occur, is 0.17. They're now asking me to find the probability of B. Now they're telling me about B complement, they're asking about B. I know the only formula that relates B and B complement is the probability of B plus the probability of its complement equals 1. Now if you look at the formulas earlier in these notes, you could actually find a formula directly for probability of B. Feel free to use that. The reason I keep coming back to this formula is if you memorize just this formula, then all you need is a little bit of algebra and you'll be able to solve each problem. So you can either remember the 3 separate formulas for each case, or you could remember this original formula and then just algebraically manipulate to get what you're looking for. So here I started with information about B complement is 0.7. I'm going to substitute that here. We're looking for the probability of B, don't know that yet. Plus 0.17 is equal to 1. If I'm going to solve this, I need to subtract 0.7 from both sides. And from that, we will get that the probability of B is equal to 0.83. So the probability that B will occur is 0.3, and the probability that it won't occur is 0.17. So in this next example, we have a sample of 700 cell batteries was selected. So we've got a sample of 700. Exactly 24 of the batteries were determined to be defective. What is the complement of the defective batteries? So if 24 batteries were defective, let's call that event D. So D is 24. Now notice they're not asking for the probability of the complement, they're just asking for the complement. So the event D complement is the not defective batteries from the sample. And as we think through this, we know you're looking at all 700 batteries. Each battery is either defective or not defective. Of the 700, 24 were identified to be defective. That means the remaining batteries were not defective. So to find the complement D superscript C, I would take the total number minus the defective ones, and what's left over is the not defective ones. And we would get 676 for that. So as they just asked for strictly the complement, the number in the complement, that's 676. If they asked a follow-up question, what's the probability of battery was not defective, we would take the number of not defective, 676, divide it by the total of 700, and that's how we'd get probability. So as you're reading through the problems, read carefully and make sure, are they asking you for the probability of the event, or are they just asking you for the number of elements in that event itself? We'll soon talk about our next set of formulas. And just as before, I'd like to begin with the visualization so that you can kind of get an idea why this formula works. Now again, remember, this is just extra information. If it helps you, keep it in mind. If not, just make sure you remember the formulas that we'll soon introduce, and you work through the problems that we have later in the video showing you how to use the problems. So what we see here is our Venn diagram visualization. As we talked about previously in this earlier video, a rectangle represents the universal set U, and everything that's considered is inside this universal set. So everything under consideration is in the rectangle. Now in this diagram, I've got 2 circles inside the rectangles. Circle A, which I see here, and circle B, which we see here. Now A and B are what are known as subsets of the universal set. And interesting thing for us to note is that A and B overlap. They've got this overlap right here. So elements among this overlap are part of both A and B. Now in set theory, there is a formula that allows you to count how many elements are in what's called A union B, which is written in symbols as A union B. So the symbol for union looks like this capital U. Now A union B by definition is everything in A plus everything in B plus everything that was in A and B, making sure that as you count, there's no overcounting in any category. So it's an exact count of everything in A plus B without overcounting. Let's look at this formula from set theory. And then A union B is where both of these circles are either separately or overlapping. The number of elements in A union B is the number of elements in A, which I'll shade that here, plus the number of elements in B, which we'll shade. And notice when I shaded the number of elements in B, do we see that this middle section that is shared by A and B got counted both in the number of elements in A and then counted again in the number of elements in B, which is why the formula continues to say minus the number of elements in A intersect B. Now, there's a direct translation of this formula, which was just counting number of elements in a set, into the idea of probability, where probability is the number of ways what we're looking for occurs divided by the total. So the translation of this idea in terms of probability is the probability that A or B occur is the probability that A occurs by itself plus the probability that B occurs by itself minus the probability that both A and B will occur. And this will be a particularly helpful formula. And that's what we see here. If A and B are any two events, then the probability that A or B occurs is the probability that A occurs plus the probability that B occurs minus the probability of A and B occurring. Now this was all predicated on the idea that A and B would have some overlap, but if we recall back to set theory, there were sets that had no overlap, and those were known to be disjoint sets, so let's draw that. If A and B are completely separate sets, which is the definition of disjoint, another word for disjoint is mutually exclusive. They are mutually excluding each other. Then this probability formula is simplified. So in the particular case where there's no overlap between A and B, if A and B are mutually exclusive, same meaning as disjoint, then the formula becomes the probability of A union B is still the probability of A plus the probability of B, but whenever we come to subtract the probability that we have A and B, by definition there is no overlap between these sets. So remember, if there's no overlap, there's no possibility that we would have both A and B at the same time, and the probability of an impossible event is 0. So we end up subtracting 0, but subtracting 0 doesn't do anything, so we just write the simpler formula that the probability of A union B in the case of disjoint events is just the probability that A occurs plus the probability that B occurs. Now, most commonly you will use this formula because commonly we don't know if events are disjoint or not, but if you ever have the extra piece of information that they are disjoint, then you can use this formula as a shortcut. But keep in mind this one will be the more commonly used of the two. So imagine I have this set that has elements 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We are going to select only one number from this set. So if it helps you kind of visualize this, imagine I have this bag, and inside the bag are pieces of paper with one has a 1. We have a 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 pieces of paper, each with one of these numbers written on them. And imagine we put our hand in the bag and only select one of the papers and then pull it out. So that's what's happening in this situation. We are looking for, based on this situation, the probability that one of the following events would occur. So our first example, what is the probability that the number I selected is odd or a multiple of 4? So in terms of solving these problems, you're going to look for some common keywords. So when we see the word or, that's a huge indication that we need to use this formula. The probability that A or B occurs is the probability that A occurs plus the probability that B occurs by itself minus the probability that they both occur at the same time. So when we read the word or, we need to begin to think and write down this formula. Now in our example, let's say the number being odd is called our A event, multiple of 4, that's called our B event. So let's just write this out. If A is the idea of being odd, look at our list of numbers 1 through 10 and write down in this subset what are the odd numbers. One, 3, 5, 7, and 9 are the odd numbers. So I've taken my entire list of outcomes and I've only written down the ones that are odd. So in fact, the probability that A occurs is the total number of outcomes, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total outcomes. I could have drawn any of the 10 slips of paper. But if I want it to be odd, I would want to have drawn either the 1, 3, 5, 7, or 9. So there's 1, 2, 3, 4, 5 acceptable outcomes. So the probability that A occurs is 5/10. Next, let's write down what's the probability that B occurs. So B is taken to be the multiples of 4. And whenever it's multiples of any number, you always start at the number in question. So multiples of 4, we start at 4. And I say, okay, 4 times 1 is 4. I've already written that down. Next, I multiply that number by 2. So 4 times 2 is 8. Notice 8 is in the list. So we write that down. 4 times 1, 4 times 2. Next up would be 4 times 3, but 4 times 3 is 12. And notice our largest number is 10, so nothing else is in the list. So the only multiples of 4 are in this set are 4 and 8. So the possible ways that could occur for us is we have our probability that we get a multiple of 4 is there's 2 ways out of the 10 ways. And now before we use this formula, I need to ask myself, could A and B occur at the same time? Well, let me re-highlight what our odd numbers are. 1, 3, 5, 7, 9. In blue, I have highlighted the odd numbers in the possible outcomes. In green, I've highlighted the multiple of 4s of the possible outcomes. Is there any overlap between these two sets? No. There is no odd number that's also a multiple of 4. So the probability that A and B occurs at the same time is 0 because there's no possible overlap. So our formula is the probability that I get an odd number, our A category, or a multiple of 4, our B category, is the probability that A occurs, which was 5/10, plus the probability that B that occurs is 2/10, minus the probability that they both occur, which we know is 0. So that's why we don't really have to write the minus here. This is an example of a disjoint set A and B. So overall, the probability that one or the other would occur is 7/10. So next up, we have the same starting scenario. We have 10 numbers, of which we will select one randomly. And now we're asked to compute what's the probability that the number is even or a multiple of 3. So as soon as we see the word or, that's our key word to tell us we should be thinking of this formula. The probability that A or B occurs is the probability that A occurs plus the probability that B occurs minus the probability that A and B occur. And remember, every time you see this in a problem, write down this general formula. It's going to do a few things. One, it's going to help you be more consistently correct in your answers. And two, it'll help you remember this formula with greater ease because the more you write it down in the right context, the more your brain is linking the probability that something or something occurs is based on this idea. Now, a recommended way of dealing with this problem is to always write down, based on your given situations, how could you meet this idea of selecting an even number? So I'm going to say the first event A is getting an even number from the list. And the total ways that I could get an even number, well, let's select those. That's 2, 4, 6, 8, or 10. Those are all even numbers within the list, so those are 2, 4, let's use the same color. So the probability that A occurs is there's 1, 2, 3, 4, 5 allowable outcomes out of the 10 possibilities, so 5/10. Next up, we'll look that we get a multiple of 3. That will be our second outcome, B. Now remember, for multiples of 3, you start at 3, and then you say, okay, 3 times 1 is 3. 3 times 2 is, think about it, and then keep going out until you've exited the list. So I'll give you a moment to write out what are all the multiples of 3 within our list of digits from 1 to 10. 3 times 1 is 3. 3 times 2 is 6, which is in the list. 3 times 3 is 9, which is in the list. 3 times 4 is 12, which leaves the list because our largest value was 10. So I've got 3, 6, and 9. So there are 3 ways that B, which is getting a multiple of 3, could occur out of the 10 ways. And then particularly here, since I've been highlighting as I've selected the numbers, I hope we can see that 6 is in both the even numbers and the multiple of 3 list. So in this case, there is overlap between the two groups. One item is in the even numbers and at the same time in the multiple of 3. So since there's one item in the overlap, the idea that A and B occur is the option 6. Probability is always the number of ways it could occur, which is one way out of the 10 ways. So then to finish up the problem, we know the probability that I would get an even number or a multiple of 3 is the number of ways that I could get an even number, which is 5/10, plus the number of ways that I could get a multiple of 3, which is 3/10, minus the number of ways that I could have both at the same time, which was 1/10. Now, all of these have the same denominator. So whenever you add or subtract fractions, if they have the same denominator, you copy that denominator again. And then I have 5 plus 3 is 8, minus 1 is 7. We end up with 7/10. So in our next example, we have that Amy plans to spend 1 to 6 hours on her homework. Let X represent the number of hours that will be spent on a given night. And unlike many of our past examples where we actually had to calculate all the probabilities, in this example, we've already been given a table that corresponds to X. All of the values at the top row are the number of hours that could have been studied a night. So for instance, if she studied 5 hours, the probability that that occurs is 0.1. Instead, if she studied 2 hours, the probability that that occurs is 0.1. This is how we would read the table. Notice the bottom row is listed as the probability that X occurs, and it's already listed out. So in this problem, when we've already been given what's called a probability distribution, they've already told us the probability for the different outcomes X. We are not necessarily calculating individual probabilities, but instead we're going to answer more generalized questions. So we're asked to find the probabilities that she would spend the following options. So we're asked, what's the probability that she would spend fewer than 3 hours studying? Well, this idea of fewer than 3 hours actually must be translated in context. What is fewer than 3 hours? The possible outcomes for amount spent studying is 1, 2, 3, 4, 5, or 6 hours. There's no other possibilities in this problem. That's all that's allowed here. So which of these numbers, 1, 2, 3, 4, 5, or 6, is fewer than 3? Well, that's 1 or 2. Both 1 and 2 are fewer than 3. So the probability that we would have fewer than 3, notice in this context, everything is naturally disjoint or separated, because if she spends 1 hour or 2 hours, there's no overlap between those two. It's either 1 hour spent studying or 2 hours spent studying. Similar to all the others, there's no overlap between 1 hour of studying and 6 hours studying. Those are separate ideas based on our table distribution. So the probability that she spends 1 or 2 in this case, since they're disjoint, is the probability of 1 hour plus the probability of 2 hours, which is, we already know the probability of 1 is 0.5, plus the probability of 2 hours is 0.1, adding those together, and we get 0.15. So let's do the next one together. What's the probability that she'd spend more than 2? Again, this is a phrase that needs to be translated in context. Remember, the possibilities are 1 hour, 2 hour, 3 hour, 4 hour, 5 hour, and 6 hours. Which of those meets the criteria that it's more than 2? We would be okay with 3 hours, or 4 hours, or 5 hours, or 6 hours. And each of these are distinct, because more than 2 means it has to be greater than 2. Now we know the probability for 3 is 0.2, plus the probability for 4 is 0.4, plus the probability for 5 is 0.10, plus the probability for 6 is 0.15. We add all those together, and we get 0.85. And that would be our answer. Now, in terms of some of the material that we've learned in this video, what we've done here is what I would call the direct approach. It said more than 2, and I've just calculated how that could occur directly. However, one thing to keep in mind is if we're okay with 3, 4, 5, or 6, does it make sense that we do not want 1 or 2 hours studying? That's the only things that we're not okay with. So we know if the number of things that we do not want is smaller than the number of things we could want, by our indirect approach, we could take 1, which is all the possibilities, and then subtract out what we don't want. The probability that we get a 1, which we don't want, is 0.05, minus the probability that we get 2, which is 0.10. And when you calculate that, 1 minus 0.5 minus 0.1 is exactly the 0.85 that we found above. So this was just to illustrate in this particular problem we had 2 different approaches: calculate exactly what they're looking for, or realize if what they're not looking for is a smaller group, find what that is and subtract it from 1. Either way, you'll get the same answer. So next up we have what's the probability that it would be more than 1 but no more than 5. A key detail here is translating what that means, so take a moment to think in context. If we have options 1, 2, 3, 4, 5, and 6, which of those meet the criteria of being more than 1 but no more than 5? To be more than 1, we can't be 1 itself, but we could be 2, we could be 3, we could be 4. Now, no more than 5 means 5 or less. So 5 would be our last option. The probability that 2 occurs, we already know, is 0.1, plus the probability that 3 occurs is 0.2, plus the probability that 4 occurs is 0.4, plus the probability that 5 occurs is 0.1, and that would be 0.1 plus 0.2 plus 0.4 plus 0.1. That's 0.8, and that would be our answer here. Now, if you wanted, this is how we would say the direct approach, because we just calculated exactly what they asked for. But in writing that, I realized that what they asked for actually has almost all the possibilities. What are the only things that we do not want in this case? We do not want a 1 or a 6. So alternatively, a second way to solve this problem would be to take 1, the total possibilities, and subtract out what we do not want, which is 0.5 probability for the 1, minus a 0.15 probability for the 6, and we get 0.8 as expected, either way. So remember, 2 different ways to solve it. Choose what makes sense to you. Now our next criteria is at the bottom of the screen. How many ways can we get fewer than 5 hours? So what's allowed in fewer than 5 in context? fewer than 5 is less than 5. So 1, 2, 3, 4. So in terms of we're okay with the probability that 1 occurs, 2 occurs, 3 occurs, or 4 occurs. So we could add all these together. 0.5 or 0.5 plus 0.1 plus 0.2 plus 0.4, that's 0.75. So the probability that we have fewer than 5 is 0.75. And then our final question here is, what is the probability that we have 6 or fewer hours? Now 6 or fewer is 6 or less. So we'd be okay with 1, 2, 3, 4, 5, or 6 as our outcome. But notice when I start to add those together, that's the entire list. So the probability that something occurs that includes the entire list, you're certainly going to get one of those outcomes. So since I know it's the probability of the entirety of the problem, I could just know the answer is 1, because the probability that a certain event or the entire outcome could happen is 1. Or I could add each of these individual probabilities together since we were okay with any of them occurring, and I'll see that I get 1. And the probability is 1, or it's a certain event that she will study 6 or fewer hours. Now our next example says find the probability that a single card drawn from a standard 52 card deck will be a diamond, or, we see the word or, face card. So whenever we're dealing with probabilities and the words or, we automatically write down the formula, the probability that A or B occurs is the probability that A occurs plus the probability that B occurs minus the probability that they both occur. And now I just need to calculate what is probability of A, what is the probability of B, what is the probability of A and B, and then format it in this correct equation. Now to help us visualize this, let's bring forth our card diagram that we've seen earlier in these notes. So the probability that we get a diamond, I'll say that is D for diamond. We see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 diamonds. So 13 out of the 52 is the probability of a diamond. The probability that we get a face card, let's call that F. For face card, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 face cards. So that's 12 out of 52. Now let me highlight what we've seen so far. The diamonds I'm going to highlight in purple. So we had each of these 13 cards are our diamonds. Now I'm going to highlight the face cards in green. These 12 cards were our face cards, and particularly with the highlighting, do you see that the diamonds and the face cards have an overlap? Specifically, these two groups overlap with the Jack of Diamonds, the Queen of Diamonds, and the King of Diamonds. So in terms of what is the number of diamonds and face cards, what's their overlap, there are 3 cards in the overlap. So it's 3 out of 52 cards is our overlap. Then we use our formula. The probability that I would get a diamond or a face card is the probability that I get a diamond, which is 13 over 52, plus the probability that I get a face card, which is 12 over 52, minus the probability that I get a diamond or face card, and face card, which is 3 over 52. All of these have the same denominator, so we know with fractions you keep the same bottom number. And then we do the operation said to the top numbers. So 13 plus 12 is 25, minus 3 is 22. And our answer would be 22 over 52. So particularly with problems that involve OR, I think it's very helpful to first write down our general formula for OR, and then find each of these pieces separately, and at the very end, add them and subtract them in the proper order. So in our next example, we've got 20 elective courses. Emily will, of the 20, enroll in one of the courses, and she's going to choose that randomly. Of the 20 courses, we have the following categories. 8 are considered recreational. 9 are what she would consider interesting courses. And 3 are what she would consider at the same time both recreational and interesting. We're asked to find the probability that the course she chooses will have at least one of these attributes. Now we know the phrasing of at least one must be translated. At least one means one or more of the attributes. So if we're looking for at least one of the attributes, that means we're okay if it's just recreational. Let's say R is recreational, I is interesting. It's okay if it's just recreational, or just interesting, or recreational and interesting. Because since there's only 2 attributes, to be more than one of those attributes would be to be both of those attributes at the same time. There's no greater possibility since there's only 2 attributes being listed. So visualizing what we're talking about, when I'm saying just recreational, in this context of only recreational, or those classes that were only recreational, just interesting would be those classes that were only interesting. And then recreational and interesting is these. Now taken together, we wanted any of these outcomes, so we're adding them all together. And you see when we add together all these possibilities, we get exactly the recreational union interesting set. So we are looking for what is the probability that it's recreational or interesting, because we know that's anything that's recreational, interesting, or both. Now we know the formula for the probability that something or something occurs is the probability that the first thing occurs plus the probability that the second thing occurs minus the probability that they both occur at the same time. And I think we have information about all of these things. Remember, there's 20 courses possible. Of those, 8 are recreational. So the probability that it's recreational is 8 out of the total 20. Plus, now I encourage you pause the video, complete the problem, unpause to check your work. We know the probability that something interesting occurs. 9 were interesting, so 9 out of the same 20 courses. Minus the fact that they were both recreational interesting were 3 courses. 3 of the 20 have been counted in both categories, so we subtract it once. All the bottom numbers are the same, so fractions, the bottom number stays the same. We add 8 and 9, and then we subtract 3. 8 plus 9 is 17, minus 3 is 14 out of 20. Now in this example, as we read through, it says the probability of A is 0.3, the probability of B is 0.4, the probability of A and B is 0.2. And just as a small extra piece of information, often if we want to write and symbolically, mathematically, we'll use this upside down U. So we could see it spelled out as the probability of A and B, or we could see it written symbolically as the probability of A intersect B. With that upside down U is 0.2. Then find the probability of A or B, and again, symbolically, instead of writing or as a text, we could instead write this symbol U for union. So keep that in mind. Now we know the formula that relates intersections and unions of sets and probabilities is something that we saw earlier in this video, and it's the probability that A or B occurs is equal to the probability that A occurs by itself plus the probability that B occurs minus the probability that they both occur. And in this case, I think we have all these pieces of information. Let's highlight them. Probability of A is 0.3. Probability of B is 0.4. Probability of A and B is 0.2. So putting this into our formula, we get 0.3 plus 0.4 minus 0.2, and that will be a probability of 0.5. Next, we have an example that says out of 800 large purchases made at a computer retailer, 336 were personal computers, 398 were laptop computers, 66 were printers. As a part of an audit, one purchase record is sampled at random. What is the probability that the selected single item that was purchased is not a personal computer? Now, based on this phrasing, what type of formula do you think we're looking at related to things we've talked about in this video? Do you think this is the idea of our earliest idea, complements? Or do you think this is the idea of our second, unions? It's not asking what's the probability it's in this category or this category. We know or is our giveaway sign for unions. Instead, it uses the word not. That's our key idea. So we're interested, what's the probability it's not a personal computer, which makes us think of complements. Let's call the personal computers P. So if we're looking for not a personal computer, we're looking for P complement. So we're looking for the probability. Now here I see that I would write probability of P complement. That's a little confusing. Maybe I'll call this personal computers, let's call it A. It doesn't match, but at least then we're not going to have the same letter repeated twice. So personal computers are A. We're looking at the probability of A complement. I know that probability is always the number of ways it could occur divided by the total option. And our total number is there's 800 purchases in all. To find the number of A complement, the number of not personal computers, well, here we know that our categories were personal computers, laptop computers, and printers. Now let's add these categories together to see if that adds up to our 800. So we've got 336 plus 398 plus 66, and that does indeed add up to our 800. So if I'm trying to find all of the not personal computers, what am I excluding? The number of not personal computers is equal to our total number, 800, of things purchased, minus the things from the category we want to exclude. So minus the 336 of personal computers we want to exclude. So 800 minus 336 gives us the remaining items that were not personal computers, which is 464. So our probability is 464 over 800, which gives us a probability of A complement being 0.58. So as we're thinking through this problem, we first notice it asked us for a probability, and when we're asked for probability, we think of the general formula. The probability of what I'm looking for is the number of ways that thing could occur divided by the total number of ways things could occur. So to help us strategize this, I just wrote that out. The number of things in the complement divided by the total number. Now I knew the total right off the bat was 800, so I just filled that in. Next I was left to figure out this number. What is the complement? Well, we're looking for the not personal computers. We know 336 were personal computers, so if I exclude those 336 from the overall total, we'll get what's left over, which are not the personal computers, which was 464. Divide that by 800, and that's how we got our probability. So as always, if you have questions, don't hesitate to reach out. I'll be happy to help you. Remember, you can contact me through our campus email or our online course.